right. I hope all of you are fine. In this video, I'll be discussing the very fundamental physical quantity in Newtonian physics, that is momentum, and then we will talk about conservation of linear momentum. Then we will try to solve some examples based on law of conservation of linear momentum. Now, the very first thing, momentum. Now, momentum means the quantity of motion that's present in a body. The quantity of motion that's present in a body is referred as momentum. And suppose I have a ball, its mass is m1, and I have another ball, its mass is m2. Now, both of these balls are moving with same speed or with same velocity in the same direction, but m1, the mass of the first ball, is greater than that of mass of the second ball. Now, if we have to stop the ball 1, we need more force to stop the ball 1, and we need less force to stop the ball 2. That means the motion that's there in the ball 1, the quantity of motion in ball 1 is more than that of the quantity of motion in ball 2. Now, similarly, if I take the same example where I have the two balls having the same mass. Now, their masses are same, but they are moving with different speeds, say v1 and v2. And v1 is greater than v2. Now, in this ball, the quantity of motion is more than that of this ball, because the speed with which this ball is moving, the velocity with which this ball is moving, is more with respect to v2. That means I again need more force to stop this ball, and I need less force to stop this ball. So these comparisons suggest that the quantity of motion that is present in a moving body is dependent on its mass and its velocity. So numerically, this momentum, which is a vector quantity, is the product of mass and velocity. And we have illustrated the things here, that the momentum, the quantity of the motion, is more when the mass of the body is more. Similarly, the quantity of the motion is more when the velocity of this body is more. So, to calculate the overall quantity of motion present in a moving body, we have momentum. And that momentum is the product of mass of the body and its velocity. And you can write down its unit is kilogram meter per second. Now, we are already aware about Newton's second law of motion, and we have discussed that in some previous video. And what is that Newton's second law of motion? That is the net external force acting on a system is rate of change of its linear momentum. This is Newton's second law of motion. Now we want to understand the very important conservation law. That's called conservation of linear momentum. Conservation of linear momentum. Conservation of linear momentum. What does this law states? And how we can lead to this law? We can lead to this law using Newton's second law of motion. The very first statement says that the total linear momentum of a body in an isolated system is conserved, is constant. The other way of stating law of conservation of linear momentum is that if the net external force acting on a system is zero, then the total linear momentum of that problem must remain constant, must be conserved. Now first, let us try to reach out to that mathematical formulation of conservation of linear momentum. You see, this is Newton's second law of motion, which states that the net external force acting on a body is simply time derivative of linear momentum, is simply rate of change of linear momentum. Now, in this equation, if I assume that the net external force that is acting is equal to zero. The net external force that is acting on the system is equal to zero. What does that mean from this equation? That means dP by dt must be equal to zero. That means the change of momentum with respect to the time must be zero. There must not be any rate of change of linear momentum. So I can say from this equation that P is constant. So what does it mean? It directly signifies the conservation of linear momentum. That means the conservation of linear momentum is a straightforward consequence of Newton's second law of motion. The only condition that we have to put here is that the net external force acting on that system is zero. If the net external force acting on that system is zero, then the linear momentum of that system will remain constant. Now suppose we have some particles having momentum P1, P2, P3 and so on and so forth, Pn. Their time derivative will be P1 plus P2 plus P3 plus so on and so forth. That must be the net external force that is acting on it. And what we find, for the sake of argument, that this net external force that is acting on the system of the particles is equal to 0. Now, if this is equal to 0, then this must be equal to 0. So on and so forth. It must be 0. And what does this equation signify? It signifies that the momenta of all the particles in that system must be equal to constant. P1 plus P2 plus P3 plus so on and so forth must be a constant. Because integration of 0 dt will give you a constant. So this is what is law of conservation of linear momentum. Now let us take some examples based on the law of conservation of linear momentum. Let us choose the problem of bullet and gun and bullet problem. Gun and bullet. Okay, we have a system. This system is carrying a gun. This is a gun, say for example, and there is a bullet in this gun. Okay, let me assume that mg is the mass of the gun. mb is the mass of bullet. Vg is the velocity of gun, and Vb is velocity of bullet. Now we have a system. This system is composed of a gun and a bullet. There's no external force acting on it, and there is an ignition inside. And what happens? The bullet goes out and we feel some inward momentum. So what is the net force acting on this system before the ignition is started, before the bullet is shot? The net external force acting on this system before the bullet is shot is equal to 0. So before bullet is shot, what is F external? That is 0. After the bullet is shot, what is the net momentum in that case? The net momentum in that case is m mass of the gun, velocity of the gun, plus mass of the bullet, velocity of the bullet, is equal to the F external. But there is no external force acting on this gun bullet problem. So this external force is 0. It It was 0 when the bullet was not shot. It is 0 when the bullet is shot. So, from this equation, what is the net momentum of the system? That is 0. Because the net external force before the bullet is shot is equal to 0. So, everything is at rest. The bullet is not going out. The gun is not coming back. So, the linear momentum of the system of gun and the bullet is 0. And after the bullet is shot by the gun, the net momentum is again 0. This is what is law of conservation of linear momentum. The two momenta must be equal. The momenta before the bullet is shot must be equal to the momenta after the bullet is shot. So, what will we achieve from here? We will achieve this thing. mgvg is equal to, plus mbvb is equal to 0. This is the momentum before, after the bullet is shot. This is the momentum before the bullet is shot. Okay, so this equation can give us a recoil velocity. This equation can give us a recoil velocity of gun. Now let us take an example, the same example that has been quoted here. I have a bullet and it is shot with the velocity 20 meter per second. The mass of the bullet is, say, 100 grams. The mass of the gun is, say, 1 kilogram. What I have to find? I have to find the recoil velocity of the gun. And what will be the direction of that velocity as well. Now, what the problem is, we have a gun bullet problem, okay? A bullet is shot with the velocity 20 meter per second and the mass of the bullet is 100 grams. This 100 grams should be converted into kilograms. So this is 100 by 1000 kilograms. Okay, this is 1 by 10 kilogram. And mass of the gun is 1 kilogram. And what we are supposed to calculate is the velocity with which the gun will move. And what will be the direction of that velocity? So, what is the mass of the gun? That is 1 kilogram. Alright. What is the velocity of the gun? We have to calculate that. Plus, what is the mass of the bullet? That is 1 by 10 kilogram. And what is the velocity of this bullet? That is 20 meter per second. Okay, this is the momentum after the bullet is shot. But no external force is acting on the gun and bullet system. So what was the momenta before the bullet was shot was 0. So this whole thing must be equal to 0. Alright, so what are we going to get? Vg. This is tan 1, tan 2. So this is Vg plus 2. Okay, is equal to 0. So velocity of the gun will come out to be minus 2 meter per second. So Vg, the recoil velocity of the gun in this problem will be what? It will be 2 meter per second. And there's a negative sign. The negative sign is indicating that the direction in which this gun will move will be opposite to the direction in which the bullet has moved. Therefore, the gun will move in the backward direction. So it will have a recoil velocity equal to 2 meters per second if the bullet of mass 100 grams is shot with the velocity 20 meters per second. So this is how the problems based on law of conservation of momentum can be solved.